Because if we want to know, I'm sorry, we're not talking about the distance traveled. If we want to know the distance traveled, then we're just going to double the depth of that reflector. Okay? That means our distance traveled is 2 centimeters as far as every 13 microseconds, because sound has to go there and has to come back. So 13 microsecond rule just applies to the depth of a reflector. The depth of a reflector, how deep that structure is in the body.
So coming back, what do you call that?
The reception, return time, reception, off time, remember all those synonyms meaning the sound's coming back to our reception. Okay. 13 microseconds. So, here goes our example right here, guys. So, a pulse's time of flight is 26 microseconds when a reflector is 2 centimeters deep. Of course, right? Because every 13 microseconds, sound is only traveling 13 microseconds. Every 13 microseconds, sound is only traveling 1 centimeter, rather. Okay? So, of course, it's going to be 26. So, no matter what, you can just keep adding those numbers. 13, you know, if it's traveling 5 centimeters, 13 times 5 is what? 5 is 15. What's 13 times 5, guys? 80. I don't think, is that high? 13 times 5?
No, it's 60.
65?
Yeah.
65? Okay. So that means that at 13 centimeters, you know, it's taking 65 microseconds to travel that long. No, at 5 centimeters, it's taking 65 microseconds to travel that long. Okay. But our total distance traveled of sound would be 10 centimeters, because it traveled 5 centimeters there. It's going to travel 5 centimeters back to the transducer. Okay? So, and this one I kind of messed up because I meant to like have this fade in at a certain time, and I was trying to get this done at like 1 in the morning because I'm trying to get it ready for you guys. Okay? So a pulse's time of flight is 39 microseconds when a reflector is 3 centimeters deep. Okay? Every 13 microseconds is 1 centimeter depth. So of course, if it travels 3 centimeters, 3 centimeters times 13 microseconds will give us 39 microseconds. Okay. Sweet there. So here's our little chart. This is the chart it has in the book for you guys, right here. Again, if you know the rules, you don't have to memorize this. All you have to be careful about what I'm asking you for. If I'm asking you for total distance traveled, know that you have to multiply the depth of the reflector times 2. Okay? If I'm actually the total distance travel, so I feel like a lot of times with you guys, I don't want to. Whenever I'm saying you guys, I'm just generalizing everybody. I don't want to single anybody out. So you got to read those questions carefully. Please read those questions carefully and break it down as to what it's asking. Because some questions can have a lot of misinformation that don't even matter pertain to the question, right? So be careful when you're reading the question and answer the question that they're asking you about. Okay? So again, that means that we're traveling 130 microseconds. The time of flight is 130 microseconds. That reflected depth is going to be 10 centimeters. 10 centimeters times 13 microseconds gives us 130 microseconds. Also, the total distance traveled would be 20 centimeters. And here you can see it right here, guys. I made this illustration because I really liked it a lot, because it's showing you right here that you're accounting for the go and return time when we're talking about the distance traveled. Okay, so keep this chart, or like I said, you don't have to memorize this. If you know the rule and know how the 13 microsecond rule applies, 13 microseconds, 1 centimeter of depth. Okay, reflected depth times 2 reflected depth. Okay, so know that. That's the most important thing about this chapter right here. Knowing how to apply the 13 microsecond rule. Okay. That's why I put these formulas up here. The depth, the speed of sound multiplied by the time of flight divided by 2. That's how we determine the depth of the reflector. Because when we're talking about the depth, like Pat said, we're not accounting for the go and return time. We're just accounting for how deep that structure is in the body. Sweet deal. All right. So you guys remember we were talking about PRP about 3 chapters ago, chapter 4, and we know how imaging depth, adjusting our imaging depth affects our PRP and our PRF. Imaging depth is what related to PRP? Directly related to the PRP, right? If I increase my imaging depth, I'm also increasing the time from the beginning of one pulse to beginning of the next pulse. Okay? Because we have to account for that listening time. Because remember, that's all we're changing when we're changing our PRP. When the pulse duration is already set, right? The manufacturer already made the pulse duration. We don't never control that. We only control this line right here, which is just the listening time. So, deep imaging, of course, is going to have a longer PRP, but then we're going to have a lower PRF, right? Because we're not getting this, our pulses aren't as frequent as they will be with this shallow imaging right here. Okay? So, adjusting the ultrasound system's maximum imaging depth, the pulse repetition period is altered. Also, the pulse repetition frequency is altered, but we're focused on PRP right now. PRP, we're good there on PRP, guys? Imaging depth and PRP? Okay? So, again, guys, I do want to write that down for us again because I really want us to know this. I'm going to write depth. These are all our parameters with pulse sound, right? PRP, PRF, and duty factor, which is just a percentage of transmit time, correct? Pulse duration over the PRP will give us that duty factor, correct? All right, so when I'm talking about relationships, if my depth increases, I'm looking at deeper imaging. How they're related to my PRP? I mean, it's also going to increase, okay? Our PRF? Decreasing because PRP and PRF, they're reciprocals, right? They're inversely related, just like period and frequency, okay? Even though they have no relationship to each other, okay? And our duty factor? Decrease. Duty factor and PRF, they're best buds. Depth and PRP, they're best buds. Always remember that. Always remember that. So if you gotta write that down on your test when you get ready to take it or what have you, even though we already took that test, but I still want you guys to know that relationship because duty factor, that's always gonna come up. It's always gonna come up. PRP, PRF, everything has to do with, especially with pulse repetition frequency, that has to do with the amount of energy going to the patient. If my pulse repetition frequency goes up, then that patient dose also goes up, right? Because I'm sending more energy into that patient in a less amount of time. Okay. All right. So PRP again, the start of one pulse to the start of the next pulse. PRP, the red right here on the deep imaging, and the green right here on the shallow imaging. The start of one pulse to the start of the next pulse. Okay. Real quick, guys. What's this right here?
Duration.
Pulse duration, right? What's this right here? What is the if this was 1 second right here, this was 1 second and ended right there, what is my frequency right here?
1 over.
What's the frequency if this was 1 second right here? What is my frequency of this sound?
2 megahertz.
1 second. It'd be 2 hertz, right? Remember, frequency is the number of pulses per second. I'm not asking you what the PRF is.
Right.
I'm just asking you what the frequency, the number of pulses. It's 1, 2 pulses in that time. So it's only our frequency is 2 hertz. Okay, 2 hertz. What's our PRP if this was PRF? If this was 1 second? 4 hertz. 4 hertz. Because I'm PRF, I'm actually about the number of pulses per second. Yeah. It just depends on where I decide to put the number. If I ended it right here, what's our PRF? 3 hertz. Guys, don't forget your units. What is what's our frequency in this 1 second?
It's
6 hertz. 6 hertz. Okay, so I'm saying that for a reason to make sure, because like I said, I was taking a practice test. Boom, I didn't read the question carefully, and I was answering in PRF. Okay, so I'm passing that on because I made that mistake. So pay attention to what the question is asking. Okay.
So the pulse is how many sets of this whole thing called frequency, right? This is pulse. This is pulse.
Yeah, all of these are pulse.
Frequency is how many times it goes up and down and goes back to
Cycle per
cycles.
second.
Per
So
second.
yeah, so that's
Cycles
2
per
cycles
second.
each.
It's 2 cycles in each of these pulses. 2 cycles in each of those pulses. Okay. Boom. So when we adjust our depth right here, guys, what are we changing? Our listening time, right? We're changing our listening time, right? We are changing the depth. We're increasing or decreasing the depth. I know that, but what specifically are we changing? Okay. just our listening time, okay? So the post-repetition period, in essence, is the go and return time, right?
Mhm.
Because it's one on time, one off time, right?
Mhm.
Think about it. The post-repetition period is the go and return time. It is the time of flight because it consists of one transmission, one reception, right? One on, one off. So essentially, our PRP is equivalent to our go and return time of our time of flight, right? Okay. So, between the transducer and the bottom of the image, the 13 microsecond rule will apply if we know the PRP as well. Okay. We have a formula for that right here, guys. So mathematically in soft tissue, the PRP is equal to the imaging depth times the 13 microsecond rule. Okay, times 13 microseconds per centimeter. Okay. And we'll get to the problems at the end where we can work out,
It's in the homework.
it's in the homework, definitely. I gave you some problems. Guys, don't overcomplicate it. Please don't ask for any deep math problems to send home because I don't want to make it complicated. It is what it is. Every 13 microseconds, sound travels 1 centimeter. Okay? You good, President? Sweet. Okay. PRP again is equal to the imaging depth, the depth of that image, times 13 microseconds per centimeter. Alright? And I put these problems up here so when we start working them out at the end, we can apply these formulas. And we're gonna plug and play. But you do have to know those formulas to know how to find the depth, find the PRP or the PRF. Okay? So again, I kept the formula up here, guys. Our example is when the depth of view is 10 centimeters, what will be our PRP? 10 times 13 microseconds. That's going to give us our post-repetition period, right? What is our post-repetition period?
130
Let's
microseconds.
forget by units, guys.
Microsecond.
Get y'all on that. Watch, I'm gonna get y'all on the test. It's gonna be PRP is 130 microseconds. And remember, PRP is the time it takes. This one on time, one off time. Okay, one on time, one off time. The time it takes from the beginning of one pulse to the beginning of the next pulse. So again, our time of flight, COF, equivalent to the PRP. So that's a new relationship you guys have. They're directly related, you can say, right? Directly related. Okay. So, when our depth of view is set to 5 centimeters, okay? Again, we're gonna plug and play. 5 centimeters, that's our imaging depth, it's telling us our imaging depth, times the 13 microsecond rule. We already did this, right guys? Somebody already told me the answer to this. What is that? 65. We already calculated that. Boom, my post-repetition period is
65 microseconds.
Thank you, dude. Don't forget my units, brother. I appreciate you. Appreciate you. Alright, so we're good here, guys, with PRP. Remember, PRP is equivalent to the time of flight. Okay? Because our time of flight is what? Our go and return time. Okay? That's what the PRP is. It's our go and return time. And then when we get our return, our reflected sound waves, then we're gonna send out another pulse. Okay? And we're gonna keep repeating that over and over and over again. Alright? So we already, that means the PRP has a relationship with the time of flight, so does the PRF, right? Okay? So again, I know it gets kind of complicated because it's breaking numbers down, and we're gonna try to figure out why is that. Okay? So our PRP, again guys, it's the number of pulses transmitted in the body each second. Or simply stated, the number of pulses per second. Pulses per second. Okay? So, this right here, guys. It's on my hand still. What is the PRF of this this series of cycles?
300.
A series of pulses. If this is 1 second, this is 1 second. So it's gonna be, according to this, it's 3 megahertz because we're talking about ultrasound. But if I'm telling you it's 1 second, then it's basically gonna be 3 hertz, correct? 3 hertz. Alright? So the speed of sound in soft tissue is equivalent to 1540 meters per second, 154,000 centimeters per second, 1.54 kilometers per second, 1.54 millimeters per microsecond. All of those numbers, guys, do not ever,